Hi all. Today we're going to be covering section 6.2, which focuses on learning how to factor trinomials. Our learning objectives for today are the following. We'll be able to factor trinomials in the form of x squared plus bx plus c. And that's where we have that coefficient of 1 in front of our general form. There's a thinner pen here, but ax squared plus bx plus c. So whenever your a value is equal to 1, we'll learn the fun technique to factor properly. In those scenarios, we'll also learn about when our a value is greater than 1, or when it's just not equal to 1. So if it's -2 or positive 28, what do we do in those cases? And just from a visual perspective, we're going to be using what's known as our famous AC method. And then finally, our third objective, we're going to utilize factoring by substitution. So let's jump into it. Let's start off with some warm-up problems. The first problem is asking us to just find all the factors of 72. And so you kind of want to think about your factor pairs here. We have 1 times what number gives you 72? 1 and 72. Well, does 2 go into 72? It does. It goes in 36 times. Does 3 go into 72? It does. How many times does 3 go into 72? Well, 3 goes into 60 20 times. And then 60 plus 12 gives us 72. So 3 goes into 12 4 times. So 20 plus 4 gives you 24. Does 4 go into 72? It does. If 2 goes in to 72 36 times, then 4 goes in half of 36, which gives you 18. Does 5 go into 72? No, it does not. What about 6? 6 does go into 72. 6 goes in 12 times. Does 7 go into 72? It does not. Does 8? Yeah, it does. 8 goes into 72 9 times. And we already said that 9 goes into 72. We just said that 8 times. So we've completed all of our factors. These are all of them. And we're done. The second warm-up question is simply finding the product of these two binomials. We want to go ahead and utilize our FOIL method here. First, outer, inner, last. We're going to multiply 3y times 2y for our first, and that gives us 6y squared. Then our outer term, we're multiplying 3y by our outer term of 5, and that gives us a plus 15y. And then we're going to go ahead and do our two inner terms. 4 times 2y gives us a plus 8y. And then finally, our last term, we're distributing that 4 to that 5, and we get plus 20. So now let's combine some like terms here. We can combine these inner two terms. 15y plus 8y gives us a plus 23y. And then let's bring the other terms down. So our final simplified form is simply 6y squared plus 23y plus 20. And we're done. All right, let's go off to that next slide, which is a notes slide. Getting into that first objective, where we're going to be able to learn how to factor trinomials of the form x squared plus bx plus c, more specifically, that coefficient of x squared being 1. And so, how do we go about doing this? Well, all we need to know is we have to find factor pairs of c that add to our b value. So what do I mean by that? Factor pairs of c that add to the b value in our trinomial. So in this particular example below, we're looking at x squared plus 5x plus 6. Again, this is really the same as 1x squared. So our a here is 1, our b here is 5, and our c here is 6. We're trying to look for all factor pairs of 6 that add to 5. So let's first find all the factor pairs of 6. We have 1 and 6, and we have 2 and 3. So these are the only factor pairs. Now, we can manipulate these by inserting negatives wherever they will help us out. But lucky for us, we're only dealing with positive values here, so we don't even have to deal with that for this problem. So of these two possibilities, which one adds up to our b value, which is 5? It's just our second one. And so what does that give us? That gives us the numbers that we are going to insert in to our placeholders, which in any x squared plus bx plus c problem, you're always going to have this form. If you're dealing with your variable x, you are going to have your form in parentheses x, close parentheses, in parentheses x, and then the operations might change. But once you identify your factor pairs, you're just going to fill that in. So this is going to be a 2. This is going to be a 3. We know the 2 is positive. We also know the 3 is positive. And we're done. So if we were to check this using FOIL, we have x times x gives you x squared. X times 3 plus 3x. 2 times x gives you a plus 2x. And 2 times 3 gives you a plus 6. Combine the like terms in the middle. 3x plus 2x indeed gives you that 5x. And we're good. All right. So now that we covered this from a rules perspective, this is just to formalize everything a bit more and carry out the necessary steps. So first thing, you have to identify that we indeed have that a value to be 1 in our x squared plus bx plus c. The second step is to identify, okay, what are factor pairs of that c value? And then to set up these potential binomials that you're going to take the product of. And then our step after that is, after we've identified our factor pairs of c, which one of those factor pairs add up to our b? And that gives us our sort of, they're calling them m and n, but that gives us our m and n values that we can place into that placeholder that we started out with. Obviously, our last step is always to check that that indeed works and it gives us our original trinomial once again. Okay, so let's put it into practice with example 1. Lucky for us, our a value is 1 here. So let's identify our B and our C. B is equal to 11. And our C is equal to 24. So what is our setup going to look like? Well, our variable is x, so we're going to have x in parentheses, x in parentheses. We just need to figure out what goes into this placeholder here. How do we do that? We look for factor pairs of 24. 1, 24. 2 goes into 24 12 times. 3 goes in 8 times. 4 goes in 6 times. 5 doesn't go in, and then 6 we already just did, so we are done. Are there any negatives? Do we have to do some manipulation here? Nope, because we have 2 positives. So now we just need to simply ask ourselves, of these 4 different factor pairs, which one adds up to our B value? Oh, would you look at that? 3 plus 8 gives us 11. So we have a plus 3 and we have a plus 8. And that's it. If you want to check, let's check using FOIL. X times x gives you x squared. X times 8 gives you that plus 8x. 3 times x gives you the plus 3x. And 3 times 8 gives you the plus 24. Let's go ahead and combine our middle like terms. 8x plus 3x gives us that 11x. And then we'll bring everything else down. And is this what we started with? It is indeed. Therefore, our fully factored form is our x plus 3 in parentheses x plus 8. And we're done. Practice another example. This one you'll notice we're going to have to end up manipulating using some negatives. And our variable here is y, so our format is going to look like this this time around. Factor pairs of our C value. So factor pairs of 28. We have 1 and 28. 2 goes into 28 14 times. 3 doesn't. 4 goes into 28 7 times. 5 doesn't. 6 doesn't. And 7 we just did. So we're done. Of these 3, which ones, or which one, there's only going to be one, factor pair that adds up to that B value? Color code this to help you guys out again. And because this B value is negative, we're going to have to do some manipulations with negatives. Well, if we stick some negatives here, that doesn't really help us. This doesn't help. Oh, would you look at that last one? If we put both as a negative, they will give us negative 11. And if we take the product of a negative and a negative, that will give us positive 28. So we're good. We have y minus 4 and y minus 7. And that's our answer. We can check once again. This time we'll check in our head. Y times y gives you y squared. Y times negative 7 gives you negative 7y. Negative 4 times y gives you a negative 4y. These are like terms. These sum to negative 11y. Looking good. And then our last negative 4 times negative 7, positive 28. It works. We have a little notes comment at the top that says, when we factor trinomials, we must have the terms written in descending order, meaning your highest degree goes first and it goes all the way to the lowest, which in most cases will be your constant. So if we're looking at this example here, let's put it in descending order first. So we're looking at now x squared plus 2x minus 48, which is in our descending order form of ax squared plus bx plus c. can easily identify that our B is 2. And then our C here is negative 48, which is what we are going to be finding the factor pairs for. And then we can carry out the problem like we have been doing. So factor pairs of negative 48. I always like to do the positive first, and then I'll manipulate with a negative sign. So we have 1 and 48. 2 goes into 48 24 times. 3 goes into 48. Well, 3 goes into 45 15 times. And so 3 goes into 48 16 times. 4 goes into 48 12 times. 5 doesn't, but 6 does. 6 goes in 8 times. And 7 doesn't go into 48, but 8 does, but we already included 8, so we're done. And now we want to figure out, of all these factor pairs, which one adds up to positive 2. And remember, we need to put in a negative for one of these values because the product needs to be negative. So I'm looking at, okay, if we want a positive value of 2, let's look at that last one. If we make that a negative 6 plus positive 8 is 2. And negative 6 times positive 8 is negative 48. So we have it. So our setup, once again, is our whole x, and we found our factor pairs, negative 6 and positive 8. And there we go. Let's check verbally once again. X times x gives you the x squared. X times 8 gives you a positive 8x. Negative 6 times x is a negative 6x. This ends up being 2x, which is what we wanted. And then negative 6 times 8 gives you the negative 48. So it works. Right, we have another little notes / comment. And this is sort of to transition into trinomials where we don't have 1 as our a value. We may have something else. So it's sort of like the extension of this traditional method that we have been practicing for the past few examples. And you can use the AC method for any traditional example, but I personally think it's a little bit more time consuming than if you were to just look at your C and B and then make that comparison. When I say a little bit more time consuming, it's just a little more structured, very much the way they described it in our notes. So again, what visual do you want to sort of use in this case? We want to draw a big giant X, and in that top portion of our X, we're taking the product of our A and C value, and in that bottom portion, we're just writing out our B value. And then I'll describe a little bit more on how that goes. Maybe what I'll do is I'll bring that image off to the next slide as well, because we're going to be utilizing some factor by grouping here too. So we have this visual. Once we get these two numbers, we are going through the whole finding factor pairs of our AC that add to our B, and then we place those there in that middle section of the X. And then from there, we manipulate our trinomial and break up that middle term into these two values so that we can factor by grouping and then overall simplify, and last step, check. So may sound a little confusing at first, but we'll tackle this through a concrete example, and then we'll enforce our skills through more examples. Just one last note that I want to mention before we jump into our first example together. If you look at all of our three terms and you can pull out a greatest common factor, that's the first thing that should be on your mind. Pull out the GCF first, and then you can jump into factoring more strategically. If you pull out that GCF, it'll make your problem solving a lot more straightforward. Okay, let's get into it. I already sort of set up the steps for the first example, and then we're just going to be sort of like filling in the blanks a bit. So notice how I highlighted my A, B, and C accordingly so that we can easily identify that our A is 6 here, our B is 7, and our C is 2. We drew out our big giant X. So our second step is to find that product of that red and orange value, which is 6 and 2 in this case. 6 times 2 gives us 12. And then our B value, we just put as is. That's our 7. Can maybe highlight that for you down here as well. And so we finished our first, second, and third step. Now our fourth step, we want to find factor pairs of that AC, which is 12. And so all of our factor pairs, 1 and 12, 2 goes into 12 6 times, 3 goes in 4 times, and then we're done because we just did 4 in that last one. Lucky for us, we have 2 pluses, so we have no manipulation of negative signs in this example. And now of these 3 factor pairs, which one adds up to our B value, which is 7? We can clearly see it's that last one, 3 plus 4 is 7. So that's what's going to go in that intersection, which is still part of our sort of step 4 process. Once you get that, again, this is very structured, very systematic. The numbers will change, but the procedures and the steps will never change in any type of problem like this. Once you get to this step, that's where you are going to manipulate this blue value in the problem and break it up into what we highlighted in yellow. We can break that up into 3x plus 4x, because 3x plus 4x gives us 7x, right? We're manipulating it. And that's our step 5. That's how we utilize this sort of factor by grouping. I would say that's probably the most challenging step in an AC method problem. But I guarantee you, once you've completed at least 10 examples of this, both with me as well as on your own, utilizing resources like My Open Math or the workbook that I handed out to you guys, then you'll be good to go. You'll get every single AC method problem correct moving forward. So now from here, let's look at those first 2 terms. We can pull out a greatest common factor. We can pull out a 3x, and when we do, we're left with 2x plus 1. And then in that second part, that I've underlined in like that turquoise blue, we can also pull out a greatest common factor. We could pull out a 2. And then when we do, we're left with, once again, a 2x plus 1. And this is key because if you did it correctly, you would have the same values inside the parentheses. And so once we have that, we can pull that out. And then what are we left with? We're left with that 3x plus 2 that we can put into another parentheses. So our overall result ends up being, put this all in black, but in parentheses 2x plus 1, and then in parentheses that 3x plus 2. And we're done. So we very successfully completed our first AC method question where our A value was not 1, it was 6 in this case. Let's practice another example together. This time we're going to do it from scratch and we're going to go a little quicker. So we're going to set up our ACX chart. We know our A is 10 here, our B is negative 55, and our C is 70. Ooh, but what was the question that I asked you in the way beginning? Something about GCF, right? Do we have a GCF here? Yes, we do. Pull out the GCF first to make your problem easier. Could you solve AC without pulling it out? You can. It's just gonna involve a lot more factor pairs and it will be a bit more tedious. So when we pull out our GCF, which in this case is just 5, we're left with 5 times 2y squared gives us that 10y squared. 5 times negative 11y gives us the negative 55y. And then 5 times 14 gives us that positive 70. And so now we have some different A, B, and C values, some smaller values that will make our problem a little easier to solve numerically. And so we're going to use those AC values in our AC method off to the side. Our A here is 2, our C here is 14, so the product is 28, and our B is negative 11. Let's look for factor pairs of 28. One and 28, 2 and 14, 3 doesn't go in, 4 goes in 7 times, 5 doesn't, 6 doesn't, and 7 we did. So we are done. And we do have some negatives here, so we're going to have to do some manipulation with negatives. Of these 3 factor pairs, with the manipulation of a negative sign, or maybe 2 negative signs, which factor pair can add up to negative 11? The only one is that last one if we make both of them negative. And so we have negative 4 here and negative 7 here. This is sort of our key for factor by grouping. We're not going to forget about this 5. We're going to put that sort of off to the side here. But then in the middle, we keep the first value the same, our 2y squared, and we keep the second value, or that last value the same, that plus 14. But we're changing this middle sign, or middle term, to break it up. We're breaking it up into a negative, sorry about that, a negative 4y minus 7y. And now let's utilize our factor by grouping. Pull out a GCF here. We can pull out a 2y. When we do, we're left with we're left with just y minus 2. Let's pull out a GCF here. Let's pull out a minus 7. And then we're left with a y minus 2. And then we don't want to forget all of this is around a big 5. So once again, we can squish this into a parentheses, and we can factor out a y minus 2 from each term. So our final result in simplified factor form is 5 in parentheses, y minus 2, and then in parentheses, 2y minus 7. You don't have to have two sets of parentheses. You can also just write it as this. You just don't want to forget that 5 on the outside. And then we're done. Right. Let's keep trekking along. So in this sort of notes uh, page, it's just mentioning we might be dealing with some trinomials that contain two variables. And so the procedure is exactly the same, even though it looks a little bit more complicated. Uh, but every step we take is the same. The only thing you just want to consider is what is the actual variable in our trinomial, so that we can determine what our factor pairs and what our b value is in such cases. So let's go ahead and do a concrete example in how to solve a type of trinomial like this. We'll start off when our a value is 1. So we'll just look at our traditional method once again. What are our factor pairs of our c value that add to that b value? And so when you're looking at factor pairs that contain a variable, just start off with the number, and then we can do a little bit of manipulation. So factor pairs of, let's just start off with positive 9. We have 1, 9, and we have 3 and 3. Now, obviously, we're going to have a negative somewhere. We can have a negative here, or we can have it in the 1. We can have it in the 3. We know it's going to be in one of the numbers in each factor pair, and we can move that around as we please. But now let's look at this variable s squared. And so we can either put in an s squared for one of the terms and nothing for the other, or we can break up that s squared into like 1s and negative 9s, or negative 3s and positive 3s. And we're actually going to want to break it up. And the reason being is if we look at that b value, which is negative 8rs, well, our b, this is really our sort of bx, our b is negative 8s. And so of the factor pairs, when we add them up, if one was just s squared, it will never give us that variable of s. So we have to break it up for it to be s and s so that we can get the sum to be some form of s. All right, so now that we have covered that, obviously we can still move those negatives around, but let's see if either of these cases work first. Do any of these, if you add them up, you'll get negative 8s. And, would you look at that? We do here. Now let's say we put the negative for the negative 1 first, and then we would have had positive 8s. We would easily realize that we just have to move that negative to that negative 9. And then we're good to go because our format is once again going to be, our variable is r times r gives us that r squared. And then we just figured out our factor pairs are simply plus 1s and minus 9s, which is the same as just r plus s, r minus 9s. Now let's check this verbally to make sure that this is indeed correct. R times r gives you r squared. R times negative 9s gives you a negative 9rs. S times r gives us sr, which is the same as plus 1rs. These are like terms. Added together gives us that negative 8rs, which is what we needed. Excellent. And then s times negative 9s gives us a negative 9s squared, which is also exactly what we needed. So we have our factored form and we are done. Right, we have another little notes part at the top, and then we can jump into example 7. So this is just saying that some trinomials are prime, meaning that once we list all of the factor pair possibilities and we show that none of them work, then we conclude that we cannot factor this efficiently. And so let's go ahead and try this in this example now. So we are looking for, once again, factor pairs of negative 12v squared. Our coefficient of u squared is just 1, so it should look in the form of something like this. But now let's look for our factor pairs. And again, start off easy. Factor pairs of 12. 112. I'll leave some space in between. We have 2 and 6. We have 3 and 4, and we're done. And we have some negatives here, so we're going to have to use some manipulation. Just put them in randomly. And then it's v squared, but again, we want this to add up to our b value, and our b value here is negative 9v, so we're actually going to break up that v squared into v and v, because v times v gives you that v squared. But v plus v are like terms, and they'll combine very easily within one another. And now we want to see, okay, well, all of these factor pairs, which one can give you that negative 9v? Obviously, we need to possibly manipulate that negative. Instead of it being here, we can fit it over into the other term. But do any of these give you negative 9v? This gives us positive 11, or let's say we put the negative here, that gives us negative 11. This one gives us negative 4, or positive 4v. This one gives us a positive v, or let's say, and this is negative, then a negative v. So none of these work. None of these work. Therefore, this trinomial is prime. And we're done. Now, later on throughout the course, we're going to learn about quadratic formula, and we would actually know how to solve for our roots or x-intercepts when we're dealing with quadratic functions like this. But we haven't gotten to that point. We're just learning about our special factoring tools. And in an instance like that, where we need to utilize our special factoring tools and methods, we would not be able to in an example like this. Hence, we have a prime trinomial. We have another little notes slide, and this sort of jumps us into our final objective for today, which is factor by using substitution. So we have sometimes a trinomial does not appear to be in the ax squared plus bx plus c form. However, we can often make a thoughtful substitution that will allow us to make it fit into this ax squared plus bx plus c form. And this method is called factoring by substitution. It is standard to use u for the substitution, but you can really use any variable you please. And then in the ax squared plus bx plus c, the middle term has a variable x. and its square, x squared, is the variable part of the first term. So you sort of want to look for this relationship as you try to find a substitution. A lot of quartic functions, so x to the fourth or like w to the fourth or r to the fourth or q to the fourth power will involve utilizing your method of substitution in order to properly factor. So let's take a look at example 8, which, whew, what do you know, is it's a quartic function. And so this x to the fourth, well, what can we use as our substitution? We want to let u be equal to x squared, right? Because we want it to get into this general form of ax squared plus bx plus c, which means if our u is x squared, let's manipulate this so that that first term is x squared. So x squared raised to what power gives you x to the fourth? It's just raised to the second, utilizing your properties of exponents. Minus 4, and then we have, once again, an x squared, which we'll substitute as u later, and then minus 5. So wherever you see an x squared, let's replace it with a u. And when we do, we end up with u squared minus 4u minus 5, which is back down to a nice straightforward standard traditional factoring method, right? U goes here because our coefficient is just 1. What are factor pairs of -5 that add to -4? Well, first let's look at factor pairs of 5, which is just, it's prime, so we only have 1 and 5, and then let's manipulate a negative. If we want to sum to -4, we should really make that -5, or that +5 negative. And so our two factor pairs are our -5 and our +1. And if we check, u times u gives you u squared. Good. U times 1 gives you a plus u. -5 times u gives you a -5u. So this gives you -4u when we combine like terms. Excellent. And -5 times 1 gives you a -5. Good. Our check works. Now, are we done though? We can't put that as our final answer because we need to substitute it back in for x squared. So wherever you see a u, we want to replace back in your x squared. So you're looking at x squared minus 5 in parentheses, and then x squared plus 1. And I'm going to say we're done right here for now because we haven't gotten into our specialing factoring of difference of squares and bringing in our knowledge of square roots. But to just foreshadow what's to come, you could potentially factor this slightly more, which is going to be a potential test question once we've learned it together. But this is really difference of squares. This can be the square root of 5 is just square root of 5. And so we can change this into x plus square root of 5 and then x minus square root of 5. That second one, though, is prime. You cannot factor this further. So you just want to keep it as x squared plus 1. And then we're done. So that's the sort of extension to this. But we haven't learned it yet in this course. So at this point in time, I will accept that first box as a full answer. Once we've learned that second part, then moving forward, I will expect you guys to simplify it to its entirety. Okay. This is just a slide that I thought would be very helpful since we're now learning about higher degrees. We've done a lot of lessons throughout the semester focusing on linear functions and also focusing on quadratics, and we'll get into quadratics even more in depth when we eventually learn how to properly graph them. But we just saw a quartic function a few slides back, and we haven't really seen any fifth degree or sixth degree polynomials quite yet. But it's good to know the general visual of what these functions look like, and so that's why I brought in this slide. So the pattern between all of these types of functions is the fact that as you increase that exponent degree, an additional sort of hump is being added. So linear functions, we have no hump. Quadratics, we have 1. Cubics, we have 2. Quartics, we have 3. So if I were to say, okay, what about x to the 28th power? How many humps do you think it's going to have? It's always going to have 1 less than the exponent number that you're dealing with. A 6th degree has 5 humps. A 5th degree, 5 minus 1, has 4 humps, and so on and so forth. This is a really cool pattern to help you out when you do end up getting into pre-calculus, and it pops up a lot. It's really, really helpful in calculus as well. I believe this is one of our last examples. Yep. And then we'll sort of conclude today's lesson. So let's factor this expression by utilizing our substitution. And here you can clearly see that, oh, this x minus 2 would really be a phenomenal substitution for u. So let's let u be equal to x minus 2, which means wherever you see an x minus 2, let's replace it with u. And then from there, we're back to our traditional, well, not even traditional, our AC method, because our traditional AC method, because our A value here in our whole A, using AU squared plus BU plus C instead of AX squared plus BX plus C, just different variables. But our A here is 1. So what are factor pairs of our C value here? What are factor pairs of 12 that add up to B, which is 7? Well, factor pairs of 12, we have 1 and 12. We have 2 and 6. And we have 3 and 4. Operations are both plus, so we don't have to deal with any manipulation of negatives. And of these 3 factor pairs, which ones add up to 7? Our 3 and 4. So when we set up our parentheses, we're looking at u plus 3, u plus 4. Let's check verbally. U times u gives you u squared. Good. U times 4 gives you 4u. 3 times u gives you a plus 3u. These are like terms. Added together give you that 7u. Looking great. And then 3 times 4 gives you plus 12. Factoring is done, but our last step is wherever you see a u, you need to substitute back in that x minus 2. And you'll notice here that we can actually simplify a little bit more. Negative 2 plus 3 gives you a plus 1, and negative 2 plus 4 gives you a plus 2. Bring that x down. So our final result is x plus 1 in parentheses times x plus 2 in parentheses. And we're done. This last slide is just some additional workbook exercises to check out for some more practice and reinforcement for this section 6.2. Hope this was useful. Next time we'll be learning about section 6.3. All right. Have a good rest of your day. Take care.